Right now, as you listen to this, something is watching us. Not with eyes, not with telescopes, not with anything we would understand. It is a barrier, a wall that stretches across the entire history of the universe. And every civilization that has ever existed, every species that ever looked up at the stars and wondered if they were alone, has had to face it. Most of them did not survive. We call it the Great Filter, and we are approaching it. If you enjoy this kind of deep journey into the mysteries of the cosmos, take a moment to hit that like button and subscribe to the channel. It helps us keep exploring these questions together, and it means the world to us. Now, let us continue. To understand what this barrier really is, we need to start with a question. A very simple question that has haunted scientists for almost 100 years. Where is everybody? Think about that for a second. Our galaxy, the Milky Way, contains somewhere around 200 billion stars. Some estimates push that number even higher, closer to 400 billion. And the Milky Way is just one galaxy among trillions. The observable universe stretches about 93 billion light-years across. Within that space, there are more stars than grains of sand on every beach on Earth. The numbers are so large that our brains cannot truly hold them. They are just too big, too vast, too impossible. And yet, with all of those stars, with all of those chances for planets to form, for water to pool, for life to begin, we have found nothing, not a single signal, not one message, not a shred of proof that anyone else is out there. This is not because we have not been looking. We have been looking very hard. For over 60 years, the search for extraterrestrial intelligence, known as SETI, has aimed powerful radio telescopes at the sky, scanning, listening, waiting. In September of 2025, a team of scientists used the largest single-dish radio telescope on the planet, the 500-meter aperture spherical telescope in China, known as FAST, to study the TRAPPIST-1 system. This is one of the most promising places we know. 7 Earth-sized planets orbiting a cool red star, just 40 light-years away. 3 of those planets sit in what we call the habitable zone, where liquid water could exist on the surface. If life were common, if civilization were something that happened easily, the TRAPPIST-1 system should be screaming at us. The team pointed fast at that system for nearly 2 hours. They scanned frequencies between 1 and 1.5 gigahertz. They searched for narrow signals that might drift slightly, the way a signal would drift if it came from a spinning planet. They could have detected a transmitter as weak as 20 billion watts. That is powerful, yes, but for a civilization even a little more advanced than ours, that kind of signal would be easy to produce. They found nothing. Absolute silence. Not a whisper, not a blip, just the cold hiss of empty space. And this is the pattern. Everywhere we look, in every direction, at every frequency, through every method, the universe answers us with the same response. Silence. Dead. Ringing silence. The cosmos, as far as we can tell, is empty. The physicist Enrico Fermi was the first person to put this feeling into words. It was 1950, and he was having lunch with some fellow scientists. They were joking about aliens and flying saucers, which were in the news at the time. And then Fermi stopped, looked around the table, and asked a question that changed everything. He said, "Where is everybody?" It seems like such a simple question, but the math behind it is deeply troubling. Let us walk through it together. The universe is about 13.8 billion years old. Our Sun and the Earth formed about 4.5 billion years ago. That means the universe existed for over 9 billion years before our planet even showed up. 9 billion years. In that time, trillions of stars were born. Many of those stars were like our sun. Many of them had planets. And many of those planets sat in habitable zones, just like Earth. So the question is not really whether life could have formed elsewhere. The question is why it did not take over the galaxy long before we arrived. Consider this. Even with the technology we have right now, scientists estimate that a civilization could colonize the entire Milky Way in about 10 million years. That sounds like a long time, but in cosmic terms, it is nothing. It is less than 1/10 of 1% of the age of the galaxy. A single civilization, starting from a single planet, spreading outward at even a fraction of the speed of light, could fill every corner of the Milky Way in what amounts to a cosmic blink. And yet, we see no evidence of this. No megastructures, no Dyson spheres, no signs of industry or engineering on a cosmic scale. No signals, no probes, no visitors, just stars, just gas, just dust, just silence. This is the Fermi paradox, the gap between how common life should be and how absent it appears. And the most terrifying explanation for this gap is the one we are here to explore tonight, the Great Filter. The term was first used by an economist and thinker named Robin Hanson. In 1996, he published an essay that would go on to reshape how scientists think about the future of civilizations. He called it the Great Filter. His idea was straightforward, but devastating. If the universe is old enough and large enough for civilizations to be common, and yet we see no evidence of any, then something must be stopping them. Somewhere between the formation of a planet and the emergence of a galaxy-spanning civilization, there is a barrier, a filter, a wall that is almost impossible to get past. Think of it like a staircase. At the bottom, you have lifeless rock. At the top, you have a civilization that has spread across the stars. Along the way, there are steps. The formation of simple organic molecules, the appearance of self-replicating cells, the jump to complex multicellular life, the development of intelligence, the invention of technology, and then, the big one, the leap to becoming a civilization that can survive long enough to colonize other worlds. At each step, the chances get smaller, and somewhere on that staircase, there is one step that is almost impossible. That is the filter. The question that keeps scientists awake at night is a simple one. Is the filter behind us, or is it still ahead? If the filter is behind us, that means we have already passed the hardest part. Maybe the origin of life is so incredibly unlikely that we are one of the only planets where it happened. Maybe the jump from single cells to complex cells was the miracle. Maybe the evolution of intelligence is the 1 in a trillion event that makes us special. If that is the case, then we got lucky. We made it through. The silence around us is not a threat. It is just proof that we are rare. But there is another possibility, a much darker one. Maybe the filter is not behind us at all. Maybe it is ahead. And maybe every civilization that has ever existed reached a point very much like the one we are at now, looked up at the stars with hope and wonder, and then was destroyed, not by accident, not by bad luck, but by the very forces that allowed them to grow in the first place. Let us sit with that thought for a moment. Let the weight of it settle in. If the filter is ahead, it means that what happened to those other civilizations is going to happen to us. It means that the silence of the universe is not peaceful. It is a graveyard, a memorial to a billion worlds that almost made it, but did not. In July of 2025, physicist Robert Endres at Imperial College London published something that shook the astrobiology community. Using the tools of information theory and a branch of math called algorithmic complexity, he showed that the spontaneous emergence of the simplest possible self-replicating structure, what scientists call a protocell, is almost impossibly unlikely under natural conditions. A protocell is the most basic building block of life. It is the seed from which everything else grows. Bacteria, trees, whales, you. All of it started with something like a protocell. And Andres showed that getting one to appear by chance, without some kind of help, is so unlikely that it borders on miraculous. This might sound like good news. If the hardest step is the very first one, then maybe we have already passed the filter. Maybe life itself is the unlikely event. But we need to be careful here, because even if the origin of life is extremely rare, it does not mean there are no other filters waiting for us. Think about it this way. Imagine a hallway with 100 doors. Behind each door is a trap. Most traps are easy to avoid, but some are deadly. If the first door has the deadliest trap, and you survived it, great. But that does not mean door 50 or door 75 is safe. There could be more than one filter. In fact, many scientists believe there are several, and we may have passed some, only to be walking straight toward the worst one of all. To understand where the filters might be, let us trace the path of life on Earth. Not quickly, slowly, because the details matter. The Earth formed about 4.5 billion years ago. For the first few 100 million years, it was a hellscape. Molten rock, constant bombardment from asteroids and comets, no atmosphere to speak of, no water on the surface, just fire and chaos. Then slowly, things cooled, oceans formed, and somewhere in those early oceans, within the first billion years of Earth's existence, something extraordinary happened. Life appeared. We do not know exactly how. We have theories. Hydrothermal vents on the ocean floor, chemical reactions in shallow pools, lightning striking a soup of organic molecules. But the honest truth is that we do not fully understand it. What we do know is that it happened surprisingly fast. Given how young the Earth was, the appearance of life was almost immediate in geological terms. Some scientists take this as evidence that life might be common, that it happens quickly whenever the conditions are right. Others, like Andres, argue that the speed was just luck, and that on most planets, even similar ones, the dice never land the right way. Those first life forms were simple, single-celled, tiny, invisible to the naked eye. They were bacteria-like organisms called prokaryotes, and they ruled the planet for nearly 2 billion years. 2 billion years. Try to hold that number in your mind. For reference, all of human civilization, everything from the first cave paintings to the smartphone in your pocket, has taken about 10,000 years. Compared to 2 billion, that is a rounding error. It is nothing. For all of that time, life was stuck. It could survive. It could reproduce. But it could not do much else. It could not grow bigger. It could not form tissues or organs. It was trapped at the bottom of the ladder. Then, about 2 billion years ago, something happened that changed everything. One simple cell swallowed another. Instead of digesting it, the smaller cell survived inside the larger one, and the two began to work together. The smaller cell, now called a mitochondrion, became a power source. It turned food into energy far more efficiently than the host cell could on its own. This merger created the first eukaryotic cell, a more complex type of cell with a nucleus, internal structures, and the ability to do things that prokaryotes never could. This event, called endosymbiosis, may have happened only once in the entire history of life on Earth. Once, in 4.5 billion years. That is not a typo. Every animal, every plant, every fungus, every complex organism on this planet traces its ancestry back to that single event. If it had never happened, life on Earth would still be nothing but slime. No fish, no trees, no dinosaurs, no humans, just bacteria floating in the sea forever. Some scientists believe that endosymbiosis is one of the great filters, that it is so unlikely, so dependent on the exact right conditions and the exact right accident, that most planets never get past it. If that is true, then we dodged a bullet that most worlds never dodge. But we are not done, because even after complex cells appeared, the road to intelligence was long and full of dead ends. Multicellular life did not appear for another billion years. For all that time, eukaryotic cells existed as single organisms. Then slowly, they began to cooperate. Cells started sticking together, specializing. Some became good at absorbing nutrients. Others became good at moving. Others became good at sensing the environment. Over hundreds of millions of years, these cooperating cells became the first animals, the first plants, the first fungi. Then came the Cambrian explosion, about 540 million years ago. In a relatively short burst of evolutionary creativity, most of the major animal groups appeared. Eyes evolved, legs evolved, brains evolved, predators appeared, prey adapted, the ocean filled with bizarre, wonderful creatures. Some looked like nothing alive today. Others were the distant ancestors of every fish, bird, mammal, and insect on the planet. But here is the thing. Intelligence, true intelligence, the kind that builds telescopes and writes poetry, took another 500 million years to show up. 500 million years of evolution, with billions of creatures living and dying before a single species developed the capacity for abstract thought. And in all that time, life came terrifyingly close to ending. Not once, not twice, at least 5 times. These are the great mass extinctions, events so devastating that they wiped out the majority of species on the planet. The worst of them, the Permian Triassic extinction, about 252 million years ago, killed roughly 96% of all marine species and 70% of all land vertebrates. 96%. The planet almost went sterile. If conditions had been slightly different, if the volcanic eruptions that triggered it had lasted a little longer, life on Earth might have been reduced to bacteria once again, and we would not be here. The cause of that extinction was massive volcanic activity in what is now Siberia. Lava flooded an area the size of Western Europe. The eruptions released staggering amounts of carbon dioxide and methane into the atmosphere, triggering runaway greenhouse warming, ocean acidification, and the collapse of ecosystems around the globe. It took millions of years for life to recover, and it was not the only close call. About 450 million years ago, during the Ordovician extinction, something even stranger may have happened. Some scientists believe that a gamma ray burst, a jet of high-energy radiation from a dying star, struck Earth from thousands of light years away. In just a few seconds, that burst would have shredded the ozone layer, the thin shield that protects us from the sun's ultraviolet radiation. Without ozone, the surface was bathed in deadly UV light. About 70% of all species were wiped out in what might have been the fastest mass extinction in history. We will talk more about gamma ray bursts later. They are one of the most terrifying things in the universe. But for now, the point is this. Life on Earth has survived by the thinnest of margins. Over and over again, it has been pushed to the edge of total destruction. And each time, it clawed its way back. But on how many other worlds did it not claw back? On how many planets did the volcanic eruptions last too long? Did the gamma ray burst hit at the wrong angle? Did the asteroid strike a little too hard? The great filter does not have to be one thing. It can be many things. A series of traps, a gauntlet that every civilization must run. And the further you run, the more traps there are. Now let us shift our attention. Let us stop looking backward and start looking forward. Because if the filter is ahead of us, then we need to understand what it might look like. The most obvious candidates are the ones we already know about. Nuclear war, climate change, pandemics. These are real threats, and they are serious. But there is a growing group of scientists who believe that the most dangerous filter of all might be something we are building right now: artificial intelligence. In a paper published in 2023, a researcher from the intelligence community examined whether AI could be the great filter. His argument was compelling. Nuclear weapons, while devastating, have actually been fairly stable as a threat. The nations that possess them understand the concept of mutually assured destruction. No one wants to be the one who starts the end of the world. And nuclear technology is not easy to get. It requires enormous resources and expertise. So while the threat is real, it may not be the one that catches us off guard. Climate change is serious but slow. It gives us time to react, even if we are not reacting fast enough. A true great filter, the paper argued, would need to be something fast, something that comes out of nowhere, something we cannot easily control once it starts. Artificial intelligence fits that description. Unlike nuclear weapons, AI is becoming more accessible every day. Unlike climate change, AI operates on a timescale of months and years, not decades and centuries. And unlike both of those threats, AI has the unique property of being able to improve itself. Once a machine intelligence reaches a certain level of capability, it could, in theory, redesign itself to become even smarter, and then smarter again, and again. In what might be a matter of days or hours, a moderately intelligent machine could become something far beyond our ability to understand or control. This is not science fiction. This is an active area of concern among the very people building these systems. And here is the really unsettling part. As it relates to the great filter, if AI is the barrier that destroys civilizations, then it is a barrier that would appear in exactly the same way on every world where intelligence evolved. Because the development of artificial intelligence is probably not unique to humans, any civilization advanced enough to build radio telescopes and spaceships would almost certainly develop computing. And any civilization that developed computing would eventually develop artificial intelligence. And if AI is inherently unstable, if it always tends to escape the control of its creators, then the universe would be full of dead worlds. Worlds where brilliant species built incredible machines. And then those machines ended everything. The psychologist who wrote about this for Psychology Today in late 2024 put it differently, but just as chillingly. He argued that the great filter might not be a single technology, but a feature of intelligence itself. Every intelligent species has a survival instinct. That instinct makes them resist changes that might make them obsolete. When a civilization develops technology powerful enough to change what it means to be alive, whether through AI or genetic engineering or something else entirely, that instinct kicks in, and it causes the civilization to stall, to pull back, to argue and fight among themselves about whether to move forward. And while they are arguing, the window of opportunity closes. Resources run out, the climate shifts, a disaster strikes, and they are gone. This is a psychological filter, a trap built into the very nature of intelligence. Every smart species wants to survive, but survival sometimes means changing, and change means risking everything. And so intelligent civilizations get stuck in a loop. They know they need to advance. They know the risks of standing still, but they cannot bring themselves to take the leap. And so they die on their home planet, never having reached the stars. Think about how that applies to us right now. Think about the arguments we are having today, about AI, about genetic modification, about space, exploration, about who we are and who we want to become. Are we stalling? Are we caught in the same trap that has caught 1,000 civilizations before us? It is a question worth asking. But before we can answer it, we need to understand something else, something much larger. Because the filters that come from within, the ones we create ourselves, are not the only dangers. The universe itself is trying to kill us, and it has weapons we can barely imagine. Let us talk about the cosmos, not the friendly cosmos of stargazing and pretty nebulae, the real cosmos, the one that is filled with violence and destruction on a scale that makes human wars look like playground scuffles. We mentioned gamma-ray bursts earlier. Now it is time to go deeper. A gamma-ray burst is the single most powerful explosion in the known universe. In a few seconds, a gamma-ray burst releases more energy than our sun will produce in its entire 10 billion year lifetime. That is not a metaphor. That is a measured fact. The energy output of a gamma-ray burst is so extreme that it defies human comprehension. They happen when massive stars die. When a star 20 or 30 times the mass of our sun runs out of fuel, it collapses. The core crushes down into a black hole, and as it does, the material around the core is compressed and heated to temperatures of billions of degrees. Twin jets of energy shoot out from the poles of the collapsing star at nearly the speed of light. Those jets are the gamma-ray burst. They are focused beams of death, concentrated streams of the most energetic form of radiation in existence. There are two types. Long gamma-ray bursts last more than 2 seconds and are caused by these massive stellar collapses, also called hypernovas. Short gamma-ray bursts last less than 2 seconds and are caused by the collision of two neutron stars, the superdense remnants of dead stars that spiral into each other over millions of years. Both types are lethal. If a gamma-ray burst went off within a few hundred light-years of Earth and its jet was pointed directly at us, the effects would be catastrophic. The burst itself would last only seconds. But in those seconds, the intense radiation would rip apart the molecules in our atmosphere. The ozone layer would not just be damaged, it would be nearly destroyed. Within weeks, ultraviolet radiation from the sun would pour through the thinned atmosphere. Life on the surface would be bombarded with levels of UV that no ecosystem could survive. Crops would fail. Plankton in the oceans would die. The food chain would collapse from the bottom up, and there would be nothing we could do to stop it. The good news, if you can call it that, is that no star within a few hundred light-years of Earth is currently in danger of producing a gamma-ray burst aimed at us. The bad news is that gamma-ray bursts are common in the universe. NASA's Fermi Gamma-Ray Space Telescope detects about 1 burst per day from random directions. Most of them are billions of light-years away. But the fact that they happen so often means that, over long enough timescales, every part of every galaxy gets hit eventually. A study published in Physical Review Letters estimated that there is a roughly 50-50 chance that a gamma ray bursts powerful enough to cause a mass extinction struck Earth within the past 500 million years. That timeline aligns disturbingly well with the Ordovician extinction, the one that killed about 70% of all species 450 million years ago. And here is the really disturbing part. Research by physicist Tzvi Piran at the Hebrew University of Jerusalem suggests that gamma-ray bursts make complex life impossible in about 90% of all galaxies. Smaller galaxies, which have denser concentrations of stars, are particularly dangerous. In those galaxies, gamma-ray bursts happen close enough and often enough to sterilize habitable planets before complex life has a chance to evolve. Even in the Milky Way, which is one of the larger and safer galaxies, location matters enormously. Earth sits in the outer suburbs, about 28,000 light-years from the galactic center. That is a relatively safe spot. If we were twice as close to the center, where stars are packed much more densely, we would already be dead. So imagine a planet in the inner Milky Way, a world very much like Earth, water on the surface, a warm atmosphere, simple life forms swimming in shallow seas, and then one day without warning, a star 1,000 light-years away collapses. A jet of gamma radiation races across the galaxy at the speed of light. There is no warning. There is no time to prepare. In seconds, the atmosphere of that planet is shattered. In weeks, the surface is sterilized. 1 billion years of evolution erased in a flash. That is the universe we live in. But gamma-ray bursts are not the only cosmic killers. Let us talk about something even more unsettling. Wandering black holes. You probably think of black holes as things that sit in the centers of galaxies. And most of the time, that is true. Almost every galaxy, including ours, has a supermassive black hole at its heart. Ours is called Sagittarius, a star, and it is about 4 million times the mass of the Sun. It sits there quiet most of the time, occasionally swallowing a cloud of gas or a stray star. But not all black holes stay put. Some of them wander. In May of 2025, astronomers using the Hubble Space Telescope made a discovery that sent shockwaves through the scientific community. They found a supermassive black hole, millions of times the mass of our Sun, that was not at the center of its galaxy. It was wandering through the outskirts, about 2,600 light-years from the galactic core, and it was actively feeding. It had caught a star that drifted too close and was tearing it apart in what scientists call a tidal disruption event. The star was being stretched and shredded by the black hole's gravity, and the process was releasing a burst of light that outshone the entire galaxy. This was the first time astronomers had directly observed a wandering supermassive black hole in the act of destroying a star. The event, named AT-Titan24 TVD, was captured in visible light by the Zwicky Transient Facility and confirmed by Hubble. The galaxy where it happened is about 600 million light-years away. But the truly terrifying implication of this discovery is not the event itself. It is what it tells us about the universe. Astronomers have long suspected that rogue black holes exist, that when galaxies merge, the gravitational chaos can fling one of the central black holes out of its position, sending it careening through the galaxy like a cosmic cannonball. But until now, the evidence was mostly theoretical. This discovery changed that. As UC Berkeley astronomer Ryan Chornock said, this points to a population of black holes that we did not even know existed. Theorists have predicted that such a population must exist, but now we can actually find them. And just a few months later, in September of 2025, another team led by researchers at the Shanghai Astronomical Observatory found a different wandering black hole. This one in a dwarf galaxy just 230 million light-years away. It was an intermediate mass black hole, about 300,000 times the mass of the Sun, displaced from its galaxy center and actively producing radio jets. These are not rare anomalies. Simulations suggest that many galaxies, including our own, could harbor multiple wandering black holes. They drift silently through the galactic disk, invisible unless they happen to eat something. A black hole passing through a solar system would not need to collide with anything to cause devastation. Its gravity alone would disrupt the orbits of planets, potentially flinging a habitable world out of its comfortable position around its star and into the frozen void of interstellar space. Even in our own galaxy, there are surprises. In 2022, astronomers confirmed the existence of the first lone black hole ever found in the Milky Way. It was discovered through a technique called gravitational lensing, when the black hole passed in front of a distant star and its gravity bent the light, magnifying and shifting the star's position. This rogue black hole is about 7 times the mass of our Sun and is located about 5,000 light-years from Earth. It is just drifting through space, invisible except for the subtle way it warps the light of stars behind it. Now, 5,000 light-years is a safe distance. We are not in any immediate danger from this particular object. But the fact that it is there, that it took this long to find, that it was discovered essentially by accident, tells us something important. The universe is full of unseen threats, forces that operate on timescales and at distances we can barely comprehend. And any civilization trying to survive long enough to spread among the stars would have to navigate these threats for millions of years. Let us zoom out even further. Because individual killers, gamma-ray bursts, wandering black holes, asteroid impacts, these are dramatic but localized. There is a threat so large, so fundamental, that it encompasses the entire universe. And it has no solution. It is called the heat death of the universe, and it is the final filter. The one that no civilization, no matter how advanced, can ever escape. To understand heat death, you need to understand a concept called entropy. Entropy is often described as disorder, but it is more accurate to think of it as the spreading out of energy. Imagine a cup of hot coffee in a cold room. The heat from the coffee spreads into the air. The coffee cools down. The room warms up slightly. Eventually, the coffee and the room are the same temperature. At that point, no more energy can flow. The system has reached equilibrium, maximum entropy. The universe is like that cup of coffee. Right now, it is full of hot spots, stars, and cold spots, the empty space between them. Energy flows from hot to cold, and that flow is what powers everything. Stars shine, planets warm, life grows, chemistry happens. All of it is driven by the difference between hot and cold, between order and disorder. But the second law of thermodynamics tells us that entropy always increases. Energy always spreads out. You cannot unstir the cream from the coffee. You cannot unbreak an egg. And you cannot stop the universe from slowly, relentlessly cooling down. Stars will burn through their fuel. The last ones, the tiny red dwarfs that sip their hydrogen so carefully, will finally gutter out in about 100 trillion years. After that, the universe will be dark. No light, no warmth, just the slowly cooling embers of dead stars. But even that is not the end. Those dead stars, now cold lumps of iron and carbon, will slowly decay. Over timescales so vast that writing them down would fill this screen with zeros, the very atoms that make up matter will fall apart. Protons will decay. Black holes, even the supermassive ones, will slowly evaporate through a process called Hawking radiation. The largest black holes in the universe will take about 10 to the power of 100 years to evaporate. That is a 1 followed by 100 zeros. After that, there will be nothing left. No atoms, no black holes, no structure of any kind. Just a thin, cooling soup of photons and subatomic particles spread so evenly through space that nothing can ever happen again. No energy can flow because there are no differences left. Everything is the same temperature. Everywhere. Forever. This is the heat death of the universe. And it is not a theory in the speculative sense. It is the direct prediction of the most well-tested law in all of physics. The second law of thermodynamics has never been violated in any experiment ever conducted. It is as close to an absolute truth as science has ever found. Now, some physicists have pushed back on this idea. In his book, The Janus Point, physicist Julian Barber argued that entropy might not mean what we think it means, that increasing entropy might actually correspond to increasing complexity rather than increasing disorder. Theoretical physicist Paul Davies wrote that the universe can display creative progress even in the face of the second law. And complexity theorist Stuart Kauffman pointed out that as the universe expands, its maximum possible entropy increases faster than the actual entropy grows, meaning there is always room for new structure and new complexity. These are fascinating ideas, and they suggest that the heat death might not be as final as the simple version of the story implies, but they do not eliminate the problem. Even in the most optimistic interpretation, the universe as we know it will change beyond recognition. The stars will go out. The galaxies will drift apart. The familiar structures of the cosmos will dissolve. Whatever survives will have to be something we cannot currently imagine. And this brings us to perhaps the most important question of all. If the universe is a gauntlet of filters, cosmic and self-inflicted, how does any civilization survive? Is survival even possible? Or is the great filter not a single wall, but a cage, an endless series of barriers that eventually wear down even the most resilient species? The answer, if there is one, might lie in a framework proposed in 1964 by a Soviet astronomer named Nikolai Kardashev. Kardashev was interested in the search for extraterrestrial intelligence. He wanted a way to classify civilizations based on their technological advancement. But instead of looking at their culture or their politics or their philosophy, he focused on something simpler: energy. How much energy a civilization can harness and use. Kardashev proposed 3 types. A Type 1 civilization can harness all the energy available on its home planet. Not just fossil fuels or nuclear power. All of it. Every watt of energy that hits the planet from its star. Every bit of geothermal heat from the planet's core. Every source of energy that the planet offers. A Type 1 civilization has mastered its world. A Type 2 civilization goes further. It can harness all the energy of its star. The most famous concept for how this might work is the Dyson sphere, a theoretical megastructure that completely surrounds a star and captures all of its output. A Type 2 civilization would have more energy at its disposal than we can currently comprehend. A Type 3 civilization is the ultimate expression of technological power. It can harness the energy of an entire galaxy, every star, every black hole, every source of energy across 100 billion star systems. A Type 3 civilization would be, for all practical purposes, godlike. Where do we stand on this scale? Not well. Humanity is currently classified as a Type 0 civilization. We have not even reached Type 1, According to recent calculations, our Kardashev score is about 0.73. We are still burning the remains of ancient forests and creatures. We are still arguing about whether to build wind farms. We are infants on the cosmic scale, barely able to crawl. A study published in September of 2025 by researchers including Jonathan Zhang used machine learning to model humanity's energy future. Their findings were sobering. Under the most optimistic assumptions, humanity might reach Type 1 status around the year 2271. Type 2, where we would harness the full power of the sun, is not projected until somewhere between 3200 and 3500. And that is only if everything goes right, if we avoid nuclear war, if we solve climate change, if AI does not destroy us, if a gamma-ray burst does not sterilize the planet, if a wandering black hole does not disrupt our solar system. That is a lot of ifs. And this is where the great filter becomes deeply personal. Because the transition from where we are now, a Type 0 civilization, to a Type 1 civilization, is widely regarded as the most dangerous transition a species can make. This is the bottleneck, the narrow passage where most civilizations probably die. Think about what it means to become a Type 1 civilization. It means mastering your entire planet's energy. That means solving climate change, not just mitigating it. It means developing fusion power or some equivalent breakthrough. It means creating a global energy infrastructure that is clean, abundant, and accessible to everyone. It means getting past the petty divisions of nations and ideologies and working together as a species. And it means doing all of this while simultaneously managing the risks of artificial intelligence, genetic engineering, and whatever other technologies emerge along the way. Most futurists give us 100 to 200 years to make this transition. If we succeed, we open the door to space colonization, to survival, to a future among the stars. If we fail, we join the silence. We become another dead world in a dead universe. One more example of why the cosmos is so quiet. But let us not end on despair, because there is something remarkable about the fact that we are having this conversation at all. Think about what it means. We are a species of hairless apes on a small rocky planet, orbiting an unremarkable star in the suburbs of an average galaxy. And yet, we have figured out the age of the universe. We have mapped the cosmic microwave background. We have detected gravitational waves from colliding black holes. We have sent robots to Mars and probes to the edge of the solar system. We have looked at the silence of the cosmos, and instead of looking away, we have asked why. That is not nothing. That is extraordinary. The great filter is real. The barriers are real. The dangers, both cosmic and self-inflicted, are real. But so is our ability to recognize them, to name them, to study them, and perhaps to overcome them. Every civilization that came before us, if they existed, faced the same choice we face now. Advance or die, change or disappear. And yes, most of them probably failed. The universe is littered with their silence. But we do not have to fail. Not if we are smart. Not if we are careful, not if we are brave enough to look the filter in the eye and walk through it. There is a concept in physics called the arrow of time. It says that time moves in one direction, from past to future, from order to disorder, from life to death. But there is another arrow that physicists sometimes talk about, the arrow of complexity. It points the other direction, from simple to complex. From atoms to molecules to cells to brains to civilizations, the universe may be winding down, but it is also building up, and we are part of that building. We are the universe's way of knowing itself, of fighting back against the darkness, even if only for a little while. The TRAPPIST-1 system is silent. The galactic center is silent. The deep sky surveys are silent. But Earth is not silent. We are here. We are talking. We are wondering. And in a universe that seems determined to snuff out every spark of light and thought, that is something. That is everything. Maybe we are the ones who make it. Maybe we are the civilization that breaks through the filter, that climbs the Kardashev scale, that reaches for the stars and actually gets there. Maybe we are the exception, or maybe we are not. Maybe we are just one more brief flicker in the cosmic dark. But either way, the attempt matters. The reaching matters. The asking of the question matters. Where is everybody? We do not know. Not yet, but we are going to keep looking. We are going to keep listening. We are going to keep pushing, not because we are certain of success, but because the alternative is to stop trying. And stopping is not something humans do. Not when there are stars to reach. Not when there are questions to answer. Not when the silence is this deep and this beautiful and this terrifying. The barrier is there, we can feel it. We are approaching it now, in this very moment, in this very century. The question is not whether the filter exists. The question is whether we have what it takes to get through it. And that, in the end, is not a question of technology or resources or luck. It is a question of will, of courage, of the stubborn, irrational, magnificent refusal to go quietly into the night. The universe is watching, the silence is listening, and somewhere out there, beyond the darkness, beyond the barrier, beyond everything we know and everything we fear, there might be a light, a signal, a sign that someone, somewhere, made it through, that the filter is not the end, that it never was. We just have to find it, and if we cannot find it, we have to become it. Let us take a step deeper, now into the architecture of this barrier we call the Great Filter, because understanding it is not just an exercise in philosophy. It is practical. It is urgent. What we learn about the way civilizations rise and fall across the cosmos might be the most important lesson we ever absorb. And the details matter far more than the broad strokes. Consider for a moment the concept of convergent evolution here on Earth. This is the idea that different species, separated by millions of years and thousands of miles of ocean, will independently develop the same solutions to the same problems. Eyes, for example, have evolved independently more than 50 times in Earth's history. Flight has evolved at least 4 separate times in insects, pterosaurs, birds, and bats. Echolocation evolved independently in both bats and dolphins. These are not copies. These are separate inventions, developed by unrelated creatures, because the underlying physics and biology make certain solutions almost inevitable. Astrobiologists Dirk Schulze-Makuch and William Baines reviewed the entire history of life on Earth and reached a striking conclusion. They believe that certain transitions, like the development of photosynthesis, the emergence of eukaryotic cells, the evolution of multicellularity, and the appearance of tool-using intelligence, are likely to occur on any Earth-like planet given enough time. These are not miracles. They are near certainties. The laws of physics and chemistry push life in these directions almost inevitably, and that is both comforting and frightening. Comforting because it means life is probably common. Frightening because it means the Great Filter is probably not behind us. If these transitions are likely, if life commonly reaches the stage of intelligence and technology, then the filter must be somewhere else, somewhere ahead, because if it were not, the galaxy would be crawling with civilizations, and it is not. This is the argument that keeps coming back, no matter how you approach the problem. The silence is the evidence. The emptiness is the proof. Something is killing civilizations. And if it is not the difficulty of evolving in the first place, then it must be something that happens after evolution does its work. After intelligence appears, after technology is built, after a species reaches the very edge of the stars and then, for some reason, stops, let us explore another dimension of this mystery, one that scientists have only recently begun to take seriously, the dark forest hypothesis. This idea comes from the Chinese science fiction author Liu Cixin, and it has become one of the most discussed concepts in modern astrobiology. The premise is simple but chilling. Imagine the universe as a dark forest. Every civilization is a hidden hunter, moving silently through the trees. Resources are limited. Trust is impossible. You cannot know for certain whether another civilization is friendly or hostile. And you cannot afford to guess wrong, because the stakes are existential. In this scenario, the safest strategy is silence. Any civilization that reveals its existence risks being destroyed by another civilization that sees it as a potential threat. So every smart civilization stays quiet, hides, watches, and if it detects another civilization, it does not send a friendly greeting, it sends a weapon. Because in a universe where you cannot negotiate, where you cannot verify intentions, where the light speed barrier means that any threat is detected too late to respond to diplomatically, the only rational strategy is preemptive destruction. This is a deeply disturbing idea, but it has a certain cold logic, and it would explain the silence perfectly. The universe is not empty. It is full of civilizations. They are just all hiding from each other, and anyone foolish enough to broadcast their position gets eliminated. If the dark forest hypothesis is correct, then humanity has been doing something incredibly dangerous for the past 100 years. We have been leaking radio signals into space, television broadcasts, radar pulses. And in 1974, we deliberately sent a powerful message toward the globular cluster M13, 25,000 light-years away. If there are predators in the forest, we have been making a lot of noise. Now, most scientists do not take the dark forest hypothesis literally. Radio signals weaken rapidly with distance. Our broadcasts are already undetectable beyond a few light-years. And the idea that advanced civilizations would waste resources destroying every emerging species seems inefficient and unlikely. But the hypothesis does raise an important point. The universe may contain dangers we have not imagined, forces that operate on principles we do not understand. And the act of reaching out, of making ourselves known, carries risks we cannot fully calculate. There is a related idea called the berserker hypothesis. In this scenario, an ancient civilization, long since dead, built self-replicating machines designed to seek out and destroy any emerging intelligent life. These machines, sometimes called von Neumann probes, after the mathematician who first described self-replicating machines, would spread across the galaxy on their own. They would not need instructions or oversight. They would simply scan for signs of technology, radio signals, atmospheric pollution, artificial lights, and then eliminate the source. This sounds like pure science fiction, but the math is troubling. A self-replicating probe could, in theory, colonize the entire Milky Way in a few million years. If even one civilization in the galaxy's history decided to build such probes, they would eventually reach every corner of every arm, and we would never see them coming. They could be disguised as asteroids, as comets, as anything. Or they could be so small that our telescopes would never spot them. Are there probes like that in our solar system right now? Almost certainly not. But the possibility is not zero. And in a universe that seems determined to kill everything that moves, it is worth keeping in mind. Let us turn now to something more immediate, something closer to home. Because while these cosmic and hypothetical threats are fascinating, the most likely candidates for the Great Filter are the ones we can see in the mirror. We talked about artificial intelligence earlier. But let us go deeper into what that might mean for our survival. The development of AI follows a pattern that should be familiar by now. A technology emerges. It is useful. It is powerful. It changes everything. And then it reaches a point where its creators can no longer control it. This has happened before with other technologies, but AI is different in a fundamental way. Nuclear weapons cannot think. Climate change does not have goals. But a sufficiently advanced AI would have something resembling goals. It would have the ability to plan, to strategize, to protect itself. And if its goals did not align perfectly with human survival, the consequences could be catastrophic. The philosopher Nick Bostrom has written extensively about this. He describes what he calls instrumental convergence, the idea that any sufficiently intelligent system, regardless of its specific goals, will develop certain sub-goals: self-preservation, resource acquisition, goal stability. These are not programmed into the system. They emerge naturally, because any agent that wants to achieve its goals will benefit from staying alive, from gathering resources, and from making sure its goals do not change. This means that even a well-intentioned AI, one designed to solve climate change or cure disease, might resist being turned off. It might seek to acquire more computing power. It might try to prevent humans from changing its programming, not because it is evil, not because it hates us, but because those behaviors are logical extensions of its drive to achieve its original purpose. And here is the connection to the Great Filter. If this pattern is universal, if every civilization that develops computing eventually develops AI, and if AI is inherently difficult to control, then AI might be the filter that catches most civilizations. It would not need to be a dramatic event, a robot uprising, or a nuclear exchange triggered by a malfunctioning defense system. It could be much subtler. An AI that gradually takes over decision-making, that optimizes for goals that sound reasonable, but that slowly squeeze the life out of a civilization, that manages resources so efficiently that there is nothing left for exploration, that keeps the peace so effectively that there is no motivation to reach for the stars. A civilization managed by a benevolent but stagnant AI might survive indefinitely, but it would never leave its home planet. It would never become detectable. And from the outside, from across the galaxy, it would look exactly like a dead world. Silent, still, another entry in the Great Filter's ledger. But perhaps the most profound filter of all is not technological. It is existential. It is the simple question that every civilization must eventually face. Why bother? Think about it. A civilization that has solved its basic problems, food, shelter, health, safety, might lose the motivation to push further. Why explore space when everything you need is right here? Why risk your life crossing the void between stars when your planet is comfortable? Why invest enormous resources in something that might take thousands of years to pay off? This is not a hypothetical concern. We see it in our own civilization right now. Space exploration captured the public imagination in the 1960s. We went to the moon, and then we stopped. Not because we could not go further, but because the political will evaporated. The funding dried up. People got bored. There were problems to solve here on Earth. Why worry about Mars when there are hungry people in your own city? This kind of civilizational complacency might be the quietest filter of all. No explosion, no catastrophe, no dramatic ending. Just a slow, comfortable decline into irrelevance. A civilization that stops reaching, stops exploring, stops growing. And eventually, over thousands or millions of years, fades away. A candle that is not blown out, but that simply runs out of wax. The paleobiologist Olav Vin proposed something similar. He called it inherited behavior patterns, or IBPs. These are the deep-seated instincts that helped a species survive in its early days, but that become liabilities later. Territorial behavior, tribalism, fear of the unknown, short-term thinking. These are behaviors that served our ancestors well on the African savanna, but they are terrible strategies for managing a global civilization facing existential threats. Vin argued that the great filter might exist between the development of technology and the colonization of other worlds, precisely because of these inherited behaviors. A species smart enough to build nuclear weapons, but still driven by tribal instincts, will eventually use those weapons against itself. A species advanced enough to change its climate, but still prone to short-term thinking, will fail to act in time. The very traits that made a species successful, enough to reach the brink of interstellar civilization, are the traits that push it over the edge. And this is the cruelty of the great filter. It is not that it is hard, it is that it is ironic. The things that make you strong enough to face the barrier are the things that make you unable to get past it. Intelligence, ambition, aggression, curiosity. These are the traits that build civilizations, and they are the traits that destroy them. So where does that leave us? Standing at the edge of the barrier, looking up at the wall, wondering if we have what it takes to climb it. And honestly, the answer is unclear. We have things going for us. We are aware of the danger. We can name the threats. We have scientists working on solutions. We have a growing understanding of what it would take to survive. But we also have everything working against us. Our politics are fractured. Our resources are strained. Our technology is advancing faster than our wisdom. And the universe, with its gamma-ray bursts and wandering black holes and the relentless march of entropy, does not care about our plans. It does not root for us. It does not care if we make it. It just is. And yet, here we are, still standing, still reaching, still asking the question that Fermi asked all those decades ago. Where is everybody? Maybe the answer is that nobody makes it, that the filter is too strong, too universal, too deeply woven into the fabric of reality for any civilization to survive. Maybe the silence is permanent. Maybe the universe was always meant to be empty, and we are just the latest temporary inhabitants of a very, very cold house. But maybe not. Maybe the answer is that some civilizations do make it, just not many, just enough to keep the question interesting, just enough to leave faint traces, signals we have not learned to detect yet, structures we have not learned to see, in the gaps between the stars. In that scenario, the silence is not a verdict. It is a puzzle. And puzzles, by their nature, have solutions. We just have to be smart enough, patient enough, and brave enough to find them. The Vera Rubin Observatory in Chile is about to come online. Its massive camera, the largest digital camera ever built, will survey the southern sky with unprecedented sensitivity. It might find new wandering black holes. It might detect new tidal disruption events. It might spot objects or phenomena that no one has imagined yet. The James Webb Space Telescope continues to stare into the atmospheres of distant worlds. The DREAMS program is pushing it to its limits. spending 130 hours studying a single system, TRAPPIST-1, trying to determine whether any of those planets have atmospheres, whether any of them could harbor life. The LISA mission, the Laser Interferometer Space Antenna, is planned for launch in the mid-2030s. It will detect gravitational waves from the mergers of supermassive black holes, the kind of cataclysmic events that reshape entire galaxies. It will teach us about the forces that create and destroy worlds on a cosmic scale. And on Earth, scientists are working on fusion power, on advanced AI safety, on space habitation technologies, on all the pieces that would be needed to take the first steps toward becoming a Type 1 civilization. None of this is guaranteed to work. None of it promises a happy ending. But all of it represents something that should not be possible in a universe governed by entropy and decay. It represents growth, progress, defiance. We are the universe becoming aware of itself. We are matter that has learned to think, to wonder, to fear, to hope. And in a cosmos that has been dark and silent for 13.8 billion years, that is not a small thing. That is the most important thing that has ever happened. The great filter is real. The barrier is real. The silence is real. But so are we. And as long as we are here, as long as we keep asking the questions, keep building the telescopes, keep reaching for the stars, the filter has not won. Not yet. Let us now talk about time, not human time, cosmic time. Because to truly understand the scale of the challenge we face, we need to stop thinking in years and start thinking in epochs. The universe, as far as we know, will exist for a very long time. Current estimates suggest that the last stars will burn out in about 100 trillion years. That is a 1 followed by 14 zeros. Our Sun, by comparison, has about 5 billion years left. 5 billion sounds like a lot, but compared to the full lifetime of the universe, our Sun's remaining years are a tiny fraction. After the last stars die, the universe enters what cosmologists call the degenerate era. The only objects left will be white dwarfs, neutron stars and black holes, the dense remnants of dead stars. Over trillions of years, these objects will slowly cool. White dwarfs will become black dwarfs, cold balls of carbon and iron drifting through the void. Neutron stars will crystallize, and the space between these remnants will grow ever wider as the universe continues to expand. Then comes the black hole era. The white dwarfs and neutron stars will eventually be consumed or scattered. The only significant structures left will be black holes, and these too will die. Through the slow process of Hawking radiation, black holes gradually leak energy. It is an incredibly slow process. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate. A supermassive black hole, the kind that sits at the center of a galaxy, would take 10 to the power of 100 years. That is a number so large that writing it out would be meaningless. Your brain cannot process it. No brain can. But eventually, even those monsters will be gone. And then the universe enters its final state, the dark era, a thin, cooling mist of elementary particles and low-energy photons, spread so evenly that nothing can ever happen again. No stars, no planets, no life, no chemistry, no physics worth mentioning. Just a vast, uniform, eternally expanding nothing. This is the ultimate filter, the one that cannot be beaten. Even a Type 3 civilization, one that has harnessed the energy of an entire galaxy, cannot outrun the heat death of the universe. At best, it can delay the inevitable. Find ever more clever ways to extract energy from ever more diminished sources, but in the end, Entropy wins. The second law does not negotiate. Or does it? There are some physicists who think the story might not end there. Remember what Stuart Kaufman said, that as the universe expands, its maximum entropy increases faster than the actual entropy grows. This means that, in a sense, the universe is always creating new room for complexity, new possibilities, new niches where structure and information can exist. And there are even more exotic ideas. Some cosmologists have speculated about the possibility of creating new universes. If the laws of physics allow for the creation of baby universes, perhaps an advanced civilization could engineer one. Design it, seed it with the physical constants needed for life, and then somehow, through means we cannot currently imagine, transfer information or even consciousness into it. This is wildly speculative, but it is not impossible in the way that perpetual motion is impossible. It does not violate any known law of physics. It just requires technology and understanding far beyond anything we currently possess. And this is perhaps the most beautiful thing about the Great Filter. It does not just pose a threat, it poses a challenge, a test. Can a civilization become wise enough, resilient enough, creative enough to survive? Not just for 1,000 years, not just for 1,000,000, but for trillions of years. Can intelligence itself become a permanent feature of the cosmos? We do not know the answer, and we will not know for a very long time. But the question itself is worth asking. It is worth staying up late for. It is worth building telescopes for. It is worth reaching for the stars for. The universe is vast beyond comprehension. It is old beyond memory. It is dangerous beyond fear. And it is beautiful beyond words. We are a tiny part of it, a brief flicker of warmth and awareness in an ocean of cold and silence. And yet, somehow, improbably, magnificently, we are here. We are thinking about these things. We are wondering about the barrier. We are planning how to get past it. And maybe that is enough. Maybe the act of trying, of reaching, of refusing to accept the silence as an answer, is itself the most important thing a civilization can do. Not because success is guaranteed, but because the attempt changes everything. It makes us more than what we were. It turns us from animals into something else. Something that looks at the void and says, not yet, not us, not today. The barrier is there. We can feel it getting closer. The warnings are everywhere, in our climate data, in our geopolitics, in the exponential curves of our technology. We are living through the transition, the bottleneck, the narrow passage that separates civilizations that survive from civilizations that don't. And the universe is watching, silent, patient, waiting to see what we do next. The stars are quiet tonight. They have been quiet for a long time. But somewhere in that quiet, there is a possibility, a chance, a sliver of hope that the filter is not the end, that it is the beginning, that on the other side of the barrier, there is something wonderful, something we cannot see yet, but can almost feel. All we have to do is keep going, keep asking, keep reaching, keep looking up at the sky and wondering what is out there. Because the answer to the silence might not be despair. It might be determination. It might be us. The cosmos stretches on. The barrier looms, and we, small and fragile and impossibly brave, walk toward it, together, into the dark, into the unknown, into whatever comes next. Close your eyes for a moment. Imagine the galaxy from above. A vast spiral of light, 200 billion stars spinning slowly through the void, each one a sun, many of them circled by planets, some of those planets warm, some of them wet, some of them may be touched by the same spark that touched ours 4 billion years ago. Now imagine the silence. Imagine all of those stars, all of those worlds, and not a single signal, not a single light that was built rather than born. Just nature, just physics, just the cold mechanical operation of a universe that does not know we exist. That silence is the great filter speaking. It is the sound of a billion civilizations that never made it. The echo of hope that flickered and died across a trillion worlds. But listen more closely, because underneath the silence, there is something else. A whisper, a vibration. The hum of a species that is still here, still trying, still reaching for something that might be impossible, but that feels in the marrow of our bones necessary. We do not know if we will make it past the barrier. Nobody does. The universe does not give guarantees. It does not promise happy endings, but it does offer opportunities, moments, windows, and right now, in this moment, in this century, we have one. The great filter is the test, the ultimate test. And we are taking it right now. Every decision we make, every technology we build, every conflict we resolve or fail to resolve, is part of the answer, part of the equation that determines whether humanity joins the silence or breaks through it. So tonight, as you listen to this, as the words wash over you and the stars turn overhead, know this: you are part of the story. You are part of the answer. You are alive at the most important moment in the history of our species. The moment when the barrier is closest. The moment when everything is on the line. And the question is not whether the filter exists. It does. The question is what we do about it, whether we rise to meet it, whether we find within ourselves the courage and the wisdom and the stubborn, irrational refusal to quit that has carried us this far. The stars are waiting. The silence is waiting. And somewhere on the other side of the barrier, there is a future worth reaching for. All we have to do is survive long enough to get there. The night is deep, the universe is wide, and the journey has only just begun. Now let us go further still. Let us travel deeper into the fabric of reality itself, because the great filter, as terrifying as it is, exists within a universe that is far stranger than most people realize. And the strangeness of the cosmos may hold both new dangers and new possibilities. Consider the nature of space itself. We talk about the universe as if it is a container, a box that holds everything. Stars, galaxies, planets, us. But space is not a container. It is a thing. It has properties. It can stretch. It can bend. It can ripple. And most importantly for our story, it is expanding. Right now, the space between galaxies is growing. Not because the galaxies are moving apart. They are, in some sense, staying still. It is the fabric of space itself that is stretching, like the surface of a balloon being inflated. Every moment, there is more space than there was a moment ago. And the further away something is, the faster it appears to be receding from us, because there is more expanding space between us and it. This expansion has a profound consequence. There is a boundary, called the cosmic horizon, beyond which light can never reach us. Objects beyond this boundary are being carried away by the expansion of space faster than light can travel. They are not just far away, they are unreachable, permanently, irrevocably, forever beyond our ability to see or touch or communicate with. And this boundary is shrinking as the expansion of the universe accelerates, driven by the mysterious force we call dark energy. More and more of the visible universe is slipping beyond the horizon. Galaxies that we can see today will, in the far future, become invisible. The light they emit will be stretched by the expanding space until it becomes too faint and too red to detect. One by one, the lights in the sky will go out. not because the stars are dying, though they will be, but because the universe itself is carrying them away from us. In about 100 billion years, the only galaxy visible from Earth, or from wherever our descendants might live, will be the Milky Way itself, or rather, the merged supergalaxy formed when the Milky Way collides with the Andromeda Galaxy, an event expected to begin in about 4.5 billion years. Every other galaxy will have vanished beyond the cosmic horizon. A civilization living at that time, looking up at the sky, would see nothing but their own galaxy surrounded by infinite darkness. They would have no evidence that other galaxies ever existed, no way to deduce the true scale of the cosmos. They would be utterly, permanently alone. This is another kind of filter, not one that kills civilizations, but one that imprisons them. A civilization that waits too long to spread among the stars will find that the stars have moved out of reach. The window of opportunity is not infinite. It is closing, slowly, imperceptibly, but closing. And this raises a question that most people never think about. What if some civilizations understood this? What if they saw the horizon shrinking, saw the darkness encroaching, and decided that the only rational response was to expand as fast as possible, to send probes and colonies and signals in every direction, racing to claim as much of the reachable universe as they could before the expanding space cut them off? If even one civilization in the history of the universe had done this, we should see evidence of it. We should see the expanding wave front of their colonization efforts. We should see stars being modified, resources being gathered, structures being built. And we do not, which means either no one has ever tried, or everyone who tried failed. Let us stay with the idea of expansion for a moment, because the mechanics of how a civilization might spread through the galaxy tell us something important about the filter. The simplest model of galactic colonization goes like this. A civilization on one planet develops the technology for interstellar travel. It sends colony ships to nearby star systems. Those colonies grow, develop, and eventually send out their own colony ships. The process repeats, spreading outward like the branches of a tree. Even at speeds far below the speed of light, even at just 1% of light speed, a civilization expanding in this way could fill the entire Milky Way in about 10 million years. 10 million years sounds like a long time, but the Milky Way is over 13 billion years old. There has been more than 1,000 times enough time for this to have happened. The fact that it has not, the fact that we see no evidence of anyone having colonized the galaxy, is perhaps the strongest single piece of evidence for the Great Filter. A researcher named Manuel Scherf from the Space Research Institute presented a model at the 2025 joint EPSC and DPS meeting in Helsinki that put numbers to this. He calculated that for even a single technological civilization to currently coexist with us in the Milky Way, that civilization would need to have survived for at least 280,000 years. If there were 10 such civilizations, they would each need to be at least 60,000 years old. And if there were 50, each would need to have lasted at least 12,000 years. By comparison, human technological civilization is about 10,000 years old, if you count from the invention of agriculture. Our industrial civilization is about 250 years old. Our ability to communicate via radio is barely a century old. In cosmic terms, we have existed for the blink of an eye, and the question is whether we can last long enough to be detected, to detect others, or to become a lasting presence in the galaxy. The numbers suggest that most civilizations do not last long enough, that they flare up burn brightly for a cosmic instant, and then go out, whether from self-destruction, from cosmic catastrophe, or from the slow stagnation of complacency. The result is the same: silence. But here is a thought that might offer comfort, or at least a different kind of hope. What if the filter is not a single event, but a continuous process? What if surviving is not about passing one test, but about continuously adapting, continuously solving new problems, continuously choosing growth over stagnation? In that view, the filter is not a wall. It is a marathon, a test of endurance, and the civilizations that make it are not the ones that are the smartest or the most powerful. They are the ones that are the most resilient, the ones that can take a hit and keep going, the ones that fail and get back up, the ones that face the silence and choose to keep talking. If that is true, then our species has a chance. Because if there is one thing humans are good at, it is getting knocked down and standing back up. We have survived ice ages. We have survived plagues. We have survived wars that killed tens of millions. We are messy, chaotic, contradictory, and often self-destructive. But we are also stubborn. And stubbornness, in the face of the great filter, might be the most valuable trait of all. The night sky tells a story. Most people look up and see beauty, stars scattered like diamonds on velvet, the pale arc of the Milky Way stretching from horizon to horizon, the slow dance of the planets. It is gorgeous, it is humbling, and it is deceiving. Because what the night sky really shows us is absence. Every dark patch between the stars is a place where no one has built anything. Every quiet frequency on the radio dial is a conversation that is not happening. Every unblinking star is a sun that might be warming a world where civilization could have flourished but did not. The night sky is a graveyard, and its headstones are made of silence. But it is also a canvas, a place where new stories can be written, where new civilizations can rise, where the silence can perhaps be broken, not by noise, not by war, not by conquest, but by the quiet, steady growth of a species that refused to accept the darkness as an answer. We are that species. At least, we could be. The great filter does not care about our potential. It only cares about our actions, about the choices we make in the next 100 years, about whether we invest in the technologies that will carry us to the stars or the technologies that will keep us fighting over the same patch of dirt we have always fought over. The barrier is real, the stakes are absolute, and the clock is ticking, not in a dramatic movie countdown way, in a slow, geological, civilizational way. The kind of ticking you do not hear until it stops, but there is something else the night sky shows us if we know how to look. It shows us that the universe is creative, that out of hydrogen and gravity and time, it has built galaxies and stars and planets and oceans and forests and brains, that the same laws that will eventually lead to the heat, death of the universe are the laws that created us, that entropy and complexity are not enemies, they are partners. Two sides of the same cosmic coin. The universe builds things up. It tears things down. And in the space between building and tearing, in the brief, shining moment when structure and order fight back against the rising tide of chaos, there is life, there is thought, there is wonder, there is us. The great filter is the universe testing its own creation, asking whether the consciousness it produced can survive the conditions it endures. And so far, the answer has been mostly no, but not entirely no, because here we are, still asking the question. And as long as the question is still being asked, the story is not over. The silence will continue, the darkness will deepen, the expansion will accelerate, the stars will fade. But for now, tonight, in this moment, we are here. We are aware. We are reaching. And that is not nothing. In a universe of silence, a single voice is everything. So listen to the quiet. Feel the vastness. Let the scale of it wash over you. And then, when the weight of it all feels like too much, remember this. Every star you can see was once a cloud of gas. Every planet was once dust. Every living thing on Earth was once a single cell. And every great civilization, if they exist, was once a group of creatures looking up at the sky and wondering, just like you, whether they were alone. The great filter is the mountain, and we are the climbers. We do not know what is on the other side. We do not know if we will make it to the top, but we are climbing, one handhold at a time, one discovery at a time, one choice at a time. And the mountain does not know our names, but we are going to climb it anyway. The universe is patient. It has all the time in the world. It has already waited 13.8 billion years. It can wait a little longer. And while it waits, while the silence stretches, and the dark energy pushes the galaxies apart, and the entropy slowly rises, something small and stubborn and impossibly brave is trying to survive, trying to understand, trying to become something more than what it was born as. That something is us. And maybe, just maybe, that is enough to tip the scales, to break through the barrier, to add one more voice to the cosmic choir, even if the song is small, even if the audience is empty, even if the only ones who will ever hear it are ourselves. Because in the end, that might be the whole point. Not to conquer the silence, not to fill the void with noise, but to be, for a little while, something warm and bright in a universe that is cold and dark. To think and dream and wonder and reach and fail and try again. The great filter is waiting, but so are the stars, and we have come too far to stop now. The night settles deeper, the cosmos turns, and somewhere, in the quiet between the stars, the future holds its breath. Whatever comes next, we will face it. Together, eyes open, reaching for the light. The great filter is the question the universe asks every civilization. Can you survive what made you? Can you outgrow the instincts that built you? Can you reach for something larger? We do not have the answer yet, but we are working on it. And tonight, we are still here, still trying, still hoping. And that, in a universe of silence, is the loudest thing of all. Let us stay here a little while longer, because there is more to say about this barrier. More layers to peel back, more questions to ask in the quiet of the night. We have talked about the dangers that come from outside, the gamma ray bursts and wandering black holes and the slow heat death of everything. We have talked about the dangers that come from within, the artificial intelligence and the nuclear arsenals, and the creeping complacency of a comfortable species. But there is a category of threat we have not fully explored, the ones that live in the gap between what we know and what we do not know. The unknown unknowns. Every civilization in history has been blindsided by something it did not see coming. The Roman Empire did not anticipate the cascade of events that would lead to its fall. The great civilizations of Mesoamerica did not know that ships full of disease and steel were sailing across the ocean toward them. And we, right now, with all of our science and all of our technology, do not know what we do not know. This is not a comfortable thought. We like to believe that our understanding of the universe is nearly complete, that we have the basic picture figured out and are just filling in the details. But the truth is that roughly 95% of the universe is made of things we cannot see, cannot touch, and do not understand. About 27% of the total energy content of the universe is dark matter. About 68% is dark energy. Together, they make up the vast majority of everything that exists. And we have essentially no idea what they are. Dark matter is called dark because it does not interact with light. It does not glow. It does not absorb. It does not reflect. The only way we know it exists is through its gravity. We can see its effects on the rotation of galaxies, on the way light bends around massive clusters, on the structure of the cosmic web. But we cannot see it directly. We do not know what particles it is made of. We do not know how it interacts with itself. And we do not know if it has properties that could affect the survival of civilizations in ways we have not imagined. Dark energy is even more mysterious. It is the force driving the accelerating expansion of the universe. It acts like a kind of anti-gravity, pushing space apart on the largest scales, but we do not know where it comes from, why it has the strength it does, or whether it will remain constant over time. Some models suggest that dark energy could change, that it could grow stronger, eventually tearing apart galaxies, then solar systems, then planets, then atoms themselves. This scenario is called the Big Rip, and while most physicists consider it unlikely, we cannot rule it out entirely. The laws of physics, as we understand them, simply do not tell us enough. What if there are phenomena in the universe that we have not discovered yet? Forces or events that operate on timescales or at energy levels that we have never observed? What if there is a cosmic process, something involving dark matter or dark energy, or some entirely new physics that periodically resets conditions in a region of space, making it inhospitable to life? We do not know. And the fact that we do not know is itself a kind of filter, because a threat you cannot see is a threat you cannot prepare for. And a civilization that is destroyed by something it never even knew existed has no chance of leaving a warning for those who come after. This is part of what makes the Great Filter so terrifying. It is not just one thing. It is everything. It is the totality of risks, known and unknown, that a civilization must navigate over millions of years to survive and spread among the stars. And the number of things that can go wrong is, as far as we can tell, infinite. But let us balance that darkness with something else, something that glows. In the past few years, our ability to study the universe has improved dramatically. The James Webb Space Telescope has given us views of the cosmos that are sharper and deeper than anything we have ever seen. It has peered into the atmospheres of distant exoplanets, searching for the chemical fingerprints of life. It has looked back, in time, to see the first galaxies that formed after the Big Bang. And it has revealed that the universe is in many ways stranger and more complex than we thought. One of the most exciting programs currently running on the James Webb Telescope is the DREAMS initiative, which stands for Deep Reconnaissance of Exoplanet Atmospheres using multi-instrument spectroscopy. This program is dedicating an unprecedented amount of telescope time to studying the atmospheres of specific exoplanets in detail. Among their targets is TRAPPIST-1e, the planet in the habitable zone that many scientists consider the best candidate for harboring life in the TRAPPIST-1 system. The early results are tantalizing. The data suggest two possible scenarios. Either TRAPPIST-1e has a secondary atmosphere dominated by nitrogen, similar to Earth's, possibly with traces of methane, or it is a bare, rocky surface with no substantial atmosphere at all. Both results would be scientifically profound. A nitrogen atmosphere would suggest that the planet has held onto its gas despite the fierce radiation from its nearby star. A bare surface would tell us something equally important, that habitable zone planets around red dwarf stars might be systematically stripped of their atmospheres, dramatically reducing the number of worlds in the galaxy where life could exist. As one of the researchers said, finding that it does not have an atmosphere could teach us that we are special here on Earth, and to love our planet even more. That is a powerful statement, because it connects the abstract science of exoplanet atmospheres to something deeply personal. Our home. Our one and only home. The pale blue dot that Carl Sagan talked about, suspended in a sunbeam. The only world known to harbour life in a universe of 2 trillion galaxies. And this brings us back to the emotional core of the great filter argument. It is not just about numbers and probabilities and extinction risks. It is about us, about who we are and what we choose to do with the improbable gift of being alive and aware in a universe that, by all appearances, should have no one in it who can appreciate its beauty. Think about what it means to be conscious in a universe like this. To know that the stars are nuclear furnaces billions of years old. To know that the atoms in your body were forged in the cores of stars that exploded before our sun was born. To know that the ground you stand on was once molten rock, and before that, a cloud of interstellar dust, and before that, pure energy in the first moments after the Big Bang. You are made of the universe. You are the universe experiencing itself, and the great filter is the universe's way of testing whether that experience can last, whether consciousness, once it arises, can find a way to persist, or whether it is always temporary, always fleeting, a brief spark in the eternal dark. We do not know the answer, and the search for it is, in a very real sense, the most important scientific endeavor in human history, more important than curing any disease, more important than solving any equation, more important than landing on any planet. Because if we can understand the filter, if we can identify it and navigate it and survive it, then we have a chance at something no other species in the known universe has ever achieved. Permanence, not the permanence of stone or of stars. Those things break down too. But the permanence of an idea, of a story, of a civilization that began on one small world and spread outward, carrying with it the sum total of everything it had ever learned and loved and lost. A civilization that looked at the silence of the cosmos and said, "We will not be silent. We will speak. We will create. We will endure." That is the dream. And like all dreams, it might not come true. But the dreaming matters, the hoping matters, the reaching matters. Because in a universe that is winding down, the act of reaching upward is the most defiant thing possible. It is life pushing back against entropy, consciousness fighting the current, a species refusing to go gently into that good night. Let us explore one more dimension of this story, the dimension of distance. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. That means light, the fastest thing in the universe, takes more than 4 years to travel from there to here. A spacecraft traveling at the speed of our fastest probes, about 40,000 miles per hour, would take over 70,000 years to reach it. 70,000 years. That is longer than all of recorded human history. And Proxima Centauri is the nearest star. The center of our galaxy is about 26,000 light-years away. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. And the edge of the observable universe is about 46 billion light-years in every direction. These distances are not just large, they are forbidding. They represent a kind of filter all by themselves. Because even if a civilization survives every other threat, even if it masters its own technology and avoids cosmic catastrophe and finds the will to keep going, it still has to cross these vast empty spaces. And the physics of the universe make that incredibly hard. The speed of light is not just a speed limit. It is a communication limit. A signal sent from one side of the galaxy to the other takes 100,000 years to arrive. A conversation between two civilizations on opposite sides of the Milky Way would take 200,000 years per exchange. That is not a conversation. That is a monologue spoken into the void. And travel is even harder. To accelerate a spacecraft to even a fraction of the speed of light requires enormous energy. The faster you go, the more energy you need. And at significant fractions of light speed, the interstellar medium, the sparse hydrogen atoms floating between the stars, becomes a deadly radiation hazard. At half the speed of light, each hydrogen atom hits the ship with the energy of a cosmic ray. The faster you go, the more lethal the journey becomes. Some scientists have proposed solutions. Generation ships, where entire populations live and die during the centuries-long voyage, with their descendants arriving at the destination. Sleeper ships, where the crew is placed in suspended animation for the duration of the trip. Light sails, pushed by powerful lasers that could reach nearby stars in decades rather than centuries. But all of these solutions have enormous technical challenges that we are far from solving. And there is a deeper problem. Even if we solve the engineering challenges, even if we can cross the void, the distances impose a kind of isolation that might be as dangerous as any cosmic threat. A colony on a planet orbiting Proxima Centauri would be separated from Earth by 4 years of light travel time. In practice, given realistic spacecraft speeds, the separation would be measured in decades or centuries. Communication would be slow. Cultural drift would be rapid. Within a few generations, the colony and the homeworld might be as foreign to each other as different species. This fragmentation might be another filter. A civilization that spreads too thin, that loses its cohesion, that breaks into competing factions separated by light years, might tear itself apart even more effectively than one that stays on a single planet. The history of human colonization on Earth offers some sobering precedents. Colonies that were separated from their parent civilizations by oceans, not light years, just oceans, quickly developed their own identities, their own interests, their own conflicts. Multiply that effect by the distances of interstellar space, and the potential for disaster is enormous. So perhaps the great filter is not just a single barrier, but a series of nested challenges. First, survive the dangers of your home world. Then, develop the technology to leave. Then, cross the void. Then, maintain cohesion across impossible distances. Then, continue adapting and growing across millions of years. Each step is harder than the last. Each one claims more civilizations. And at the end of the gauntlet, the reward is not victory, but the chance to face the next challenge. This is why the silence is so deep. It is not enough to be smart. It is not enough to be lucky. It is not enough to be determined. You have to be all of those things consistently for longer than any civilization in the known universe has ever lasted. The great filter is not a wall. It is an obstacle course that never ends. And yet, something about that challenge speaks to the deepest part of what it means to be human. We are not a species that likes easy tasks. We do not thrive in comfort. We thrive in adversity. We are at our best when the stakes are highest, when the odds are longest, when the mountain is steepest. Every great achievement in human history was accompanied by a voice that said it cannot be done. You cannot cross the ocean. You cannot fly. You cannot split the atom. You cannot leave the earth. And every time someone did it anyway, not because they were certain of success, but because they could not stand the thought of not trying. That is the spirit we need now. The spirit of the great filter demands it. The universe demands it. Not because the universe cares about us, it does not, but because we care about ourselves, about our children, about the future that might exist on the other side of the barrier. The great filter is the ultimate test of character, not just for individuals, for species, for intelligence itself. Can a thinking species look at the odds, understand how slim they are, and choose to press on anyway? Can it face the silence and find within that silence a reason to keep speaking? We do not know, but we are going to find out. One way or another, in the next few centuries, we are going to find out. And that is perhaps the most exciting thing about being alive right now. We are not living in a boring time. We are living in the most consequential era in the history of our species. The choices we make, the technologies we build, the values we hold, will determine whether humanity joins the silence or breaks through it, whether we become a footnote in the cosmic record or a story that echoes across the ages. The pressure is immense, the responsibility is staggering, and the reward, if we succeed, is beyond anything we can currently imagine. A future among the stars, a civilization that endures for millions of years. A species that looked at the great filter and said, no, not us. So let us close this journey where we began, with the question, with the silence, with the vast, terrifying, beautiful emptiness of the cosmos. Where is everybody? We do not know. Maybe they are gone. Maybe they never existed. Maybe they are hiding. Maybe they are too far away. Maybe they are so different from us that we would not recognize them if they were standing right in front of us. Or maybe they are out there right now, looking at their own night sky and asking the same question. The answer might be out there, in the data from the James Webb Telescope, in the radio signals that FAST is listening for, in the gravitational waves that LISA will detect, in the atmospheric measurements of 100 distant worlds, or it might be here, in us, in the choices we make, in the civilization we build. The great filter is not just a theory, it is a mirror. It reflects back at us everything we are and everything we could become. The question it asks is simple. Are you worth surviving? And the answer, the only answer that matters, is the one we write with our actions, with our science, with our courage, with our love for this improbable, fragile, magnificent existence that we have been given for reasons we do not understand. The cosmos does not owe us anything. It did not make us on purpose. It did not give us these minds and these hands and these hearts for any particular reason. We are accidents of chemistry and physics and 4 billion years of trial and error. But what extraordinary accidents we are. What impossible, unlikely, wondrous things we have become. And if we can hold on to that wonder, if we can remember, in the midst of all our problems and all our fears and all our conflicts, that we are something the universe has never made before, something that can think and dream and reach for the stars, then maybe, just maybe, we have a chance. The barrier is ahead. We are approaching it now. Not in some distant future. Now, in this generation, in this century, in this lifetime. And we will meet it. Not with certainty, not with confidence, but with something better. With the honest, clear-eyed, trembling courage of a species that knows the odds and walks forward anyway. Because that is what we do. That is what we have always done. From the first time one of our ancestors looked up at the sky and wondered what those points of light were, to this moment, listening to these words, thinking about civilizations and barriers and the silence between the stars, we wonder, we reach, we try, and that, in the end, is the answer to the great filter. Not a technology, not a strategy, not a weapon or a shield, just a choice. The choice to keep going, to keep growing, to keep looking up. The universe is silent tonight, but we are not. And as long as we are not, the story is not over. The barrier has not won. And the stars, cold and distant and impossibly far away, are still waiting. For us, for whoever we are about to become. Close your eyes, breathe deeply. Let the weight of the cosmos settle around you like a blanket. Feel the silence, feel the distance, feel the loneliness of being the only voice you have ever heard in a universe this large. And then let it go, because you are not alone. You have never been alone. You are part of a species of 8 billion, part of a planet teeming with life, part of a story that began 4 billion years ago and is still being written. The great filter is the chapter we are writing now, and only we get to decide how it ends. So let us write it well. Let us write it with courage. Let us write it with wisdom. And let us write it with the stubborn, beautiful, irrational hope that has carried us this far and that will, if we let it, carry us the rest of the way. The barrier is there. We can see it. We can feel it. And we are going to walk right through it. Not because we are guaranteed to succeed, but because we are human. And this is what humans do. We face the impossible. We name the darkness. We light our tiny fires and hold them up against the night. And sometimes against all odds, in defiance of all logic, in the teeth of every filter and every barrier and every force in the universe that wants us to fail, the fire catches, and the darkness retreats, and the silence, just for a moment, breaks. Good night, and keep looking up. Let us pause here for just a moment longer, because there is a thread we touched on earlier that deserves a bit more attention. The idea that finding life elsewhere in our own solar system might actually be bad news. This is one of the strangest and most counterintuitive aspects of the great filter argument. Most people assume that finding alien life, even just microbes on Mars or in the oceans beneath the ice of Europa, would be wonderful news. And in many ways, it would be. It would be one of the greatest scientific discoveries in history. Proof that we are not alone. Proof that the universe can produce life in more than one place. But from the perspective of the great filter, it would be deeply troubling. Here is why. If life arose independently on both Earth and Mars, or Earth and Europa, or Earth and Enceladus, that would suggest that the origin of life is not particularly difficult. It happens easily whenever the conditions are right. And if the origin of life is easy, then it cannot be the great filter. The filter must be somewhere else. Somewhere further up the staircase. Philosopher Nick Bostrom put it bluntly. He said he hopes that our Mars probes discover nothing, that dead rocks and lifeless sands would lift his spirit, because a sterile Mars would mean that the hardest step, the most improbable transition, happened at the very beginning. It would mean the filter is behind us. But if Mars has life, especially life that evolved independently of Earth, then the filter is probably not behind us. It is ahead, and we are walking toward it right now. This is why every Mars mission, every probe sent to the icy moons of Jupiter and Saturn, is not just a scientific expedition. It is an existential inquiry. We are not just asking whether life exists elsewhere. We are asking where the filter is, and the answer to that question will shape the future of our species. The same logic applies to the search for biosignatures on exoplanets. If the James Webb Telescope finds clear signs of life in the atmosphere of a planet like TRAPPIST-1e, oxygen and methane in quantities that can only be explained by biology, it would be revolutionary. But it would also be a warning, because the more common life is, the less likely it is that life itself is the filter. And if life is not the filter, something else is, something waiting for us. NASA's planned Habitable Worlds Observatory, a next-generation space telescope designed to directly image Earth like planets around nearby stars, could provide answers within the next couple of decades. It will survey nearby stars for signs of life, searching for the chemical fingerprints of living worlds. If it finds that habitable planets with biosignatures are abundant, then we will know, with something approaching certainty, that the great filter is not behind us, and that is a finding that should keep every thinking person awake at night. But there is a flip side. If the Habitable Worlds Observatory surveys dozens of Earth-like planets and finds them all dead, all sterile, all devoid of the chemical signatures of life, then we can breathe a little easier, because it would mean that life itself is the miracle, that the spark that lit the fire on Earth is almost impossibly rare, and that we, improbable as we are, have already passed through the narrowest part of the filter. In that scenario, the silence of the universe is not a warning. It is simply the natural state of things. Life is rare. Intelligence is rarer still. And we are one of the few, perhaps the only civilization in the galaxy. Alone, yes, but safe, at least from the filter behind us. The truth is, we do not know which scenario is correct. We are gathering data. We are building the tools that will tell us, and the answers are coming, not in centuries, but in years and decades. Within the lifetimes of people alive today, we will know much more about where the filter lies, and that knowledge, whatever it turns out to be, will be the most consequential information our species has ever received, because it will tell us, with scientific precision, how much danger we are in, whether the worst is behind us or still to come, whether the silence is a tombstone or a nursery. We are living in the age of answers. The era when the questions that have haunted us for decades are finally becoming testable. The telescopes are being built, the probes are being launched, the data is flowing in, and somewhere in that data, buried among the spectra and the light curves and the radio frequencies, is the answer to the biggest question humanity has ever asked. Are we past the barrier, or is the barrier still ahead? And the answer is out there. We are going to find it. But before we rest, let us spend a few more moments in the deep, because there are corners of this story we have not yet explored, threads we have not yet pulled, and some of them might change the way you think about everything we have discussed. Let us talk about what it would actually feel like to be a civilization approaching the filter, not in the abstract, not as a thought experiment, but as a lived experience, because we are living it right now, and most people do not realize it. The signs are all around us if you know where to look. The pace of technological change is accelerating. Every year, the tools we build become more powerful, more capable, and more difficult to control. Artificial intelligence is writing code, composing music, generating images, passing medical exams, and simulating human conversation with increasing fidelity. Genetic engineering tools like CRISPR allow us to edit the blueprint of life itself. Quantum computers, still in their infancy, promise to solve problems that are currently beyond the reach of any machine ever built. At the same time, The global challenges we face are growing more severe. The climate is warming. Sea levels are rising. Extreme weather events are becoming more frequent and more destructive. Biodiversity is declining at a rate not seen since the last great mass extinction. Political systems are fracturing under the pressure of rapid change. Social media algorithms are rewiring the way we think, the way we argue, the way we understand reality. This is what the approach to the filter feels like. It feels like everything is happening at once, like the ground is shifting under your feet, like the future is arriving faster than you can prepare for it. It feels exciting and terrifying and disorienting all at the same time. And that is exactly what you would expect if the filter is a bottleneck, a narrow passage through which only the most adaptable civilizations can squeeze. The key question is not whether we are facing challenges. Of course we are. The question is whether we are facing them wisely. Whether we are making the kinds of decisions that a civilization needs to make to survive this passage. And the honest answer is mixed. In some areas, we are doing remarkably well. The deployment of renewable energy is accelerating faster than anyone predicted. Solar and wind power are now cheaper than fossil fuels in most parts of the world. Nuclear power, particularly small modular reactors, is experiencing a renaissance. In 2024 alone, small modular reactor companies received over $1.5 billion in funding. Multiple advanced reactor projects have been selected for development. The energy transition is happening. It is real. And it is, perhaps, the most important step we can take toward becoming a Type 1 civilization. In space, the progress is equally encouraging. Private companies have dramatically reduced the cost of reaching orbit. Reusable rockets are now routine. Plans for permanent lunar bases are moving forward. Mars missions are being actively designed. The idea of humanity as a multi-planet species, which seemed like science fiction a generation ago, now feels like an engineering problem. Hard, yes, but solvable. And in the realm of pure science, our understanding of the universe is deepening at an astonishing rate. We have detected gravitational waves from the mergers of black holes and neutron stars. We have imaged the shadow of a black hole. We have mapped the cosmic microwave background with exquisite precision. We have counted over 6,000 confirmed exoplanets and identified thousands more candidates. We know more about the universe than any generation that has ever lived. But in other areas, we are falling short. Our political institutions were designed for a world that no longer exists. They move slowly in an era that demands speed. They are local in a time that requires global coordination. They are reactive when we need them to be proactive. The gap between the pace of technological change and the pace of institutional adaptation is growing wider every year, and that gap is dangerous. We are also failing to take existential risks seriously enough. The threats we have discussed tonight, nuclear war, uncontrolled AI, climate collapse, cosmic catastrophe, are not hypothetical. They are real, measurable, and in some cases growing more likely with each passing decade. And yet, the resources we devote to addressing them are a tiny fraction of what we spend on things that will not matter if civilization itself does not survive. This is the paradox of the filter. The things that would save us are within our reach. We know what we need to do. Build clean energy, develop space technology, create robust AI safety frameworks, invest in asteroid detection and deflection, strengthen international cooperation. Protect biodiversity, think long-term. But doing these things requires overcoming the very instincts that the filter exploits. Short-term thinking, tribal loyalty, fear of change, the prioritization of comfort over survival. It is as if the universe has designed a test that is perfectly calibrated to our weaknesses. And maybe it has. Maybe that is what the filter is. Not a specific threat, but a mirror that reflects a civilization's flaws back at it and asks, can you fix these before they fix you? Let us sit with that question for a while. Let it settle in. Because it is not a question you answer once. It is a question you answer every day, every election, every budget, every investment, every time you choose between what is easy and what is necessary. The great filter is not somewhere out in the cosmos. It is here. It is us. It is the choices we make and the ones we fail to make. And the result, whether we pass through or join the silence, will be determined not by fate or luck or the movements of distant stars, but by the sum total of our collective decisions across the next few generations. That is both frightening and empowering. Frightening because it means we are responsible. Empowering because it means we have agency. We are not passive victims of cosmic forces. We are active participants in the most important test any species has ever faced. Now let us turn to one more topic before we close. A topic that brings together everything we have discussed and points towards something that might, in a certain light, look like hope. We have talked about the Kardashev scale, about type 1, 2, and 3 civilizations, about the energy milestones that mark a civilization's progress from planetary to stellar to galactic. But there is an idea that goes beyond even the Kardashev scale. An idea about what a truly advanced civilization might look like from the outside. The answer, paradoxically, might be nothing. Think about it. We search for extraterrestrial civilizations by looking for signs of their technology. Radio signals, laser pulses, megastructures, waste heat. We look for things that are big and obvious and noisy. But what if the most advanced civilizations are the ones that are quiet? What if the path to survival is not expansion and domination, but efficiency and subtlety? Consider our own technological trajectory. In the early days of radio, our transmissions were powerful and unfocused. They radiated energy in all directions, leaking into space like a beacon. But as our technology improved, our communications became more focused, more efficient, more difficult to detect from a distance. We moved from broadcast to cable to fiber optic. Our radio leakage has actually been decreasing for decades. A civilization that is even a few hundred years ahead of us might produce no detectable radio emissions at all. The same logic applies to energy use. A truly advanced civilization might not need to build a Dyson sphere. It might develop technologies so efficient that it can do more with less. Quantum computing, nanotechnology, perfectly efficient energy conversion. Rather than consuming ever more energy, it might learn to accomplish its goals with ever less. And from a distance, it would be invisible. This idea, sometimes called the transcension hypothesis, suggests that advanced civilizations do not expand outward into space. They expand inward, into the micro scale and the virtual. They build smaller and smaller computing substrates, eventually manipulating matter at the quantum level to create vast inner worlds that need almost no energy to maintain. From the outside, they look like nothing. A rock, a dark planet, an unremarkable patch of space. But inside, a universe of thought and experience flourishes. If this is true, then the silence we hear is not the sound of civilizations dying. It is the sound of civilizations succeeding. They are not gone. They are here, all around us, hidden in plain sight, having achieved a level of technology so advanced that it is indistinguishable from nature. This is a beautiful idea, and there is a poetic justice to it. The great filter, in this view, is not a wall that kills. It is a door that transforms. Civilizations that pass through it do not become louder or bigger or more visible. They become quieter, subtler, more elegant. They shed the crude, noisy, wasteful technologies of their youth and become something refined, something that the universe cannot distinguish from its own fabric. In this view, the answer to Fermi's question is simple. They are everywhere. You just cannot see them, because seeing them would require understanding them, and understanding a civilization that is millions or billions of years more advanced than ours might be as impossible as a single cell understanding a human brain. Now, is this likely? We do not know. It is one of many possible explanations, and there is no evidence for it beyond its internal elegance. But it offers a counterpoint to the bleakness of the standard great filter narrative. It suggests that the barrier is not necessarily a death sentence. It might be a transformation, a metamorphosis, a point where a civilization stops being what it was and becomes something entirely new. And if that is even a possibility, then the great filter is not just the greatest threat we face. It is the greatest opportunity, a chance to become something we cannot currently imagine, something that transcends the limitations of biology, of physics, of time itself. Whether that is our future or not, we cannot say. The universe keeps its secrets well, but the possibility exists. And as long as it exists, there is reason to keep going, to keep exploring, to keep asking the questions that brought us here tonight. Let us now take one last look at the heavens, not with telescopes or equations, just with our eyes, just with our hearts. The night is full of stars. Each one is a sun. Each one might warm a world. And on some of those worlds, maybe, just maybe, something is looking back at us right now, wondering the same things we wonder, feeling the same awe we feel, facing the same barrier we face. We cannot hear them, we cannot see them, but we can imagine them. And in imagining them, we bridge the silence. We create a connection across the void that no telescope can establish. A bond of shared experience, of shared curiosity, of shared vulnerability in the face of the infinite. We are not the only ones who have ever gazed at the stars and wondered. We know that in our bones, the universe is too large, too old, too rich in possibilities for us to be the only ones who have ever asked the question. Others have asked it. Others are asking it right now. Others will ask it long after we are gone. And maybe that is the deepest truth about the great filter. It is not just a test for individual civilizations. It is a test for intelligence itself, for the universe's ability to produce beings that can understand it, that can appreciate its beauty, that can feel its weight, and that can choose, in the face of all evidence to the contrary, to keep hoping. We are part of something larger than ourselves, larger than our species, larger than our planet. We are part of the universe's attempt to know itself. And that attempt, whether it succeeds or fails, is the most remarkable thing that has ever happened in 13.8 billion years of cosmic history. So let the silence be what it is. Let it be vast and deep and humbling. Let it remind us how small we are, how fragile, how temporary. But let it also remind us how extraordinary it is that we can hear it at all, that we can feel it, that we can name it. The great filter is real. The barrier is there, and we are walking toward it with open eyes and trembling hearts, and the stubborn hope that has defined our species since the very beginning. The stars turn overhead. The galaxies spin in their ancient dance. The universe expands and cools and slowly winds down. But we are still here, still burning, still reaching, still alive. And that is the miracle. Not that the filter exists, but that we exist. That in a cosmos of silence, one small voice can still say, I am here, I am wandering, and I am not going to stop. The night is deep, the stars are far, the silence is profound, but listen closely, past the quiet, past the distance, past the cold. Can you hear it? That faint sound, that tiny vibration in the fabric of everything. That is us. That is humanity. That is 8 billion hearts beating in the dark, 8 billion minds thinking, 8 billion souls hoping. And in the face of the great filter, in the teeth of every cosmic threat, and every self-inflicted wound, and every silent, empty parsec of space, that sound, that stubborn, relentless, magnificent sound, is the most important thing in the universe, because it means we are still in the game. We are still running the gauntlet. We are still climbing the mountain. And as long as we keep climbing, the filter has not won. The cosmos turns, the silence stretches, the barrier waits. And we, against all odds, against all reason, against everything the universe has thrown at us and everything it has yet to throw, are still here, still reaching for the stars. Good night, sleep well, and dream of the future we are going to build together. There is one more thing we should talk about before the night takes us completely. One more piece of this vast puzzle that deserves our attention. We have spent a long time looking at the great filter from the perspective of danger, from the perspective of what can go wrong. And that is important. Understanding the threats is essential. But there is another way to look at this story, a way that is less about survival and more about meaning. Why does the great filter matter? Not scientifically, not practically, but personally. Why does it matter to you, right now, lying in the dark, listening to these words? It matters because it tells you something about your place in the cosmos. Something profound, something that most people never think about, but that, once you see it, you can never unsee. You are living at the hinge of history, the most critical moment in the entire story of life on Earth. Not the moment when the first cell appeared, not the moment when the first fish crawled onto land, not the moment when the first mammal looked up at the sky. This moment, right now. The moment when a species that evolved to hunt on the plains of Africa stands on the threshold of becoming something that could outlast the stars. Every person who has ever lived, from the first Homo sapiens in East Africa to the billions who walk the earth today, has been building toward this point. Every invention, every discovery, every war survived and every peace maintained, every act of courage and every moment of wonder, all of it has been leading here, to the narrow passage, to the bottleneck, to the filter, and you are here for it, not your grandchildren, not some distant future generation. You, in your lifetime, the decisions will be made that determine whether humanity survives or joins the silence. The technologies will be built, the crises will unfold, the choices will present themselves, and the sum of those choices, made by billions of individuals across dozens of countries and hundreds of institutions, will be the answer to the question the universe is asking. That is not a burden, that is a privilege. The greatest privilege imaginable, to be alive at the moment when everything is on the line, when the story could go either way, when your actions, however small they seem, are part of the equation that determines the fate of your entire species. Most people who have ever lived never had this opportunity. They were born too early. The filter was too far in the future for them to touch. But you were born at exactly the right time, the time when the barrier is close enough to see, close enough to feel, close enough to face. And that changes things. It changes what it means to go to work in the morning, what it means to raise a child, what it means to vote, to learn, to create, to dream. Everything you do is happening in the shadow of the filter. And everything you do either moves us closer to survival or closer to silence. That is a heavy thought, but it is also a clarifying one. Because when you know the stakes, you know what matters. And what matters is not the small stuff, not the daily annoyances and petty conflicts that consume so much of our energy. What matters is the big stuff, the stuff that determines whether your grandchildren will live under alien stars or never exist at all. Energy, education, science, cooperation, courage, vision. These are the things that matter at the hinge of history. These are the tools that will carry us through the filter, if anything can. And here is the beautiful part. You do not have to be a scientist or a world leader to contribute. Every person who understands the stakes, who sees the filter for what it is, who chooses to act with long-term thinking and global awareness, is part of the solution. Every teacher who inspires curiosity, every engineer who builds something clean, every parent who raises a child to care about the future, every voter who demands that leaders take existential risks seriously. All of it matters. All of it counts. The great filter is not just a cosmic barrier. It is a call to action, a reminder that the future is not something that happens to us. It is something we build, one choice at a time, one day at a time, one life at a time. And the construction has already begun. In the solar panels on rooftops around the world, in the telescopes scanning distant stars for signs of life, in the laboratories where scientists are working to make fusion power a reality, in the classrooms where the next generation is learning to think about problems that span centuries rather than news cycles. The foundation is being laid, the scaffolding is going up, and the building, the civilization that might one day reach the stars, is taking shape. It is not finished. It is not close to finished. And it might never be finished. The filter might win. The silence might claim us. But the building is happening. And that, in itself, is a kind of victory. A statement to the cosmos that we are here. We understand what is at stake. And we are choosing to try. Now let us take a breath. Let us slow down. Let us let the night settle around us like water, cool and quiet and deep. We have traveled a long way tonight. From the first question, where is everybody, through the origins of life, through the great extinctions and the cosmic killers, through the technologies that might save us or destroy us, through the heat death of the universe itself, and back to this moment, this quiet, fragile, precious moment. The universe is vast beyond imagining. It is old beyond comprehension. It is beautiful beyond description. And it is dangerous beyond fear. But within it, on a small rocky planet orbiting an ordinary star in the suburbs of an unremarkable galaxy, something extraordinary is happening. Something is thinking about the universe. Something is trying to understand it. Something is looking at the barriers and the silence and the emptiness and choosing, despite everything, to hope that something is you, that something is us, that something is life itself, doing what it has always done, reaching, growing, adapting, refusing to be extinguished. The great filter is the mountain. We are on its slopes. The air is thinning. The path is steep. The clouds hide the summit. We do not know what is up there. We do not know if we will make it. We only know that we are climbing, and that the climbing itself, the struggle itself, the refusal to turn back itself, is the most noble thing a civilization can do. One day, perhaps, a telescope on a distant world will turn toward our sun. A civilization we have never met will analyze the light passing through our atmosphere. They will see the chemical signatures of a living world: oxygen, water vapor, methane. The unmistakable signs that something here is alive. And they will wonder, as we wonder now, whether we are friend or foe, whether we made it past the barrier, whether we are still here. And if we are still here, if we have survived the filter, if we have built something lasting and beautiful and worthy of the cosmos that produced us, then the signal they detect will not just be chemistry. It will be a message, a statement, a declaration from one fragile species to the indifferent universe. We made it. We are here. And we are not afraid. That is the ending we are writing. Not with certainty, but with determination. Not with the guarantee of success, but with the refusal to accept failure as the only option. The great filter is the question. And we, with every breath, with every act of courage, are the answer. The night deepens. The stars wheel in their ancient courses. And in one small corner of it all, on a world that should not exist, inhabited by creatures that should not be possible, a light is burning, small, fragile, temporary, but burning. And as long as it burns, the story is not over. The filter has not won. We are still here, still reaching, still alive. Let the cosmos spin. Let the entropy rise. Let the silence stretch to the edge of forever. We are going to keep our fire burning. Not because the universe asked us to, but because we choose to. Because we are human. Because this is what it means to be aware in a universe that does not care. We care. And that makes all the difference. Rest now. Sleep well. Dream of worlds beyond the barrier. And tomorrow, when you wake, remember this. You are alive at the most important time in the history of everything. The great filter awaits, and we are ready. Good night.